Alright, let's move on. As we've done in previous weeks, for ANOVA, steps 4, 5, and 7 basically get combined together. Because when you're doing your descriptives with ANOVA, remember we're interested in what the DV looks like at each level of the IV, which is technically bivariate. But we are also assessing assumptions at this point, because we can do this before the ANOVA. Okay, let's look at normality. So we have already talked about all of these different statistics, but it gets a little bit complicated with a 2A ANOVA. So if we look at, we can use a command called table. We can put in our two categorical variables with table. So table, pints, sex. And then as subcommands, I can say contents, n attract, mean attract, SD attract, row column. So what I'm asking for is the n, the mean, and the standard deviations for our DV across pints and sex. Pints will be placed on our rows and sex on our columns, and I'll show what this is in a second. Then we have our format. This simply is just going to set everything to 2 decimal places. I couldn't tell you why to set it to 2 decimal places. It's percentage 6.2f. It is just what it is. There we go. And so we get this table coming out. And so what we can see is up the top is the n, so how many people are in that cell. Then we have the mean of that cell, and we have the standard deviation of that cell. We also have the total means for each of our variables. So what this means is for males who had 0 pints, we had 8 of them, their average rating of a female was 66.88 units on our attractiveness scale. They had a standard deviation of 10.3. Males who had 2 pints had the exact same mean, though their standard deviation was a little bit higher. There was a little bit more variation. Males who had 4 pints, their attractiveness ratings dropped, and the standard deviations are about 10.84. The total down the bottom here is the total, it's the mean attractiveness of all males averaging across how many pints they had. So if I went 66.88 plus 66.88 plus 35.63, and I divided that by 3, I would get about 56.46 within rounding error. And it has a much larger standard deviation, 18.50. So the same can be done with females. Females with 0 pints had a mean attractiveness rating of 60 with a much smaller standard deviation than men. We see it goes up a little bit to 62.5 at 2 pints, and it drops to 57.5 at 4 pints. We see, interestingly, that the standard deviations increase as alcohol goes up, so we're seeing more variation. And then the mean amount of attractiveness rating across all females was 60.21 on a standard deviation of 6.34. Now, this total column over on the far right-hand side tells us the average amount of attractiveness rated for everyone who had 0 pints of alcohol. So we're averaging across gender now. So before we were averaging across the amount of alcohol, now we're averaging across gender. And what we see is for those who drank 0 pints, averaged across gender, they had a mean attractiveness of 63.75. If we go down to 2 pints and we average across gender, what we see is that the mean attractiveness is 64.69. And averaging across gender for 4 pints, the mean attractiveness was 46.56. Down the bottom here, in the corner, we have the grand mean. So that's if we took all of these scores, added them up and divided them by 6, I will get 58.33. This is the grand mean for the whole study. Regardless of your gender, regardless of the pints of alcohol that you had, on average, participants were rating the attractiveness about 58.33. Now, this exercise seems arbitrary. It's kind of like, well, what's the point? You know, we've just looked at all these means, that's kind of interesting, who really cares? But there's actually some really important information here. When we start looking at our two-way ANOVA, we're actually going to be looking at these means, we'll be looking at these means, but we'll also be looking at these 6 means. And we're going to be doing this through what's called main effects and interactions. So a main effect is asking whether or not there's a difference between the levels of an IV averaged across the other. So the main effect of gender would be asking whether or not the average male attractiveness rating is significantly different to the average attractiveness rating of females averaging across alcohol. So the main effect of gender is saying if we average these 3 numbers for males, we get 56.46. If we average these 3 numbers for females, we get 60.21. Is 56.46 different to 60.21? And last week, when we did one-way ANOVA, we were looking at main effects. Now, we didn't talk about them as main effects in one-way ANOVA because we weren't averaging across another variable, but it's that same kind of concept. And when we see the ANOVA table, it will be laid out the same as our one-way. The same for pints of alcohol. We'll get a main effect for this as well. And this will be asking, if we average across gender, is the mean attractiveness for people who had no pints of alcohol different if they had 2 or if they had 4, or is 2 different to 4? So it's asking if any of these means are different to the others. Now, if I was a betting man, I would say that 4 looks very, very different to 2 and is probably different to 0 as well, but that 2 and 0 look like they're the same. And so again, when we look at the main effector of alcohol, we are literally averaging across gender. You could even do this by going, well, is 66.88 plus 60.63 divided by 2 different to 66.88 plus 62.50 divided by 2? Like, you can literally do it like that if you want, because you're just going to reproduce the numbers that are already here. However, in addition to the main effects, we also have an interaction. And the interaction is going to ask, well, is the difference between males from 0 to 2 different to females at 0 to 2? And so what we can see here is that males, the difference between males who had 0 pints and males who had 2 pints, there's no difference in their mean attractiveness. But for females, we see that there is a slight increase. It's a 2-unit increase. The interaction will also go males at 0 to 4 compared to females at 0 to 4. Is this the same difference? And here we see for males, there's a 30-point drop or thereabouts in their attractiveness. For females, there's only a 3-point drop. So it seems like alcohol drastically affects males' ratings much more than females. And the fact that males' alcohol ratings are affected more than females, because our attractiveness goes from 66.88 to 35 for males, but 60 goes to 57 for females, the odds are we are going to see an interaction here. These differences are not the same. The interaction will also do 2 to 4 for both males and females and ask, well, is that difference the same? And it's not going to be. So, whilst the main effects are interested in these means on the outside, the interaction compares the numbers here. It doesn't just go males and females at every point of alcohol, it also goes the other way as well. You can ask whether or not the mean amount of alcohol for 0 points for males and females is different for males and females at 2 points. You can do the same thing at 4. So here what we'd be saying is, well, males have a rating of 66.88 at 0 points compared to females having 60, so there's a 6-point difference here. But at 2 pints, there's only a 4-point difference between genders, so it looks like they get closer together. But 0, it has its 6-point difference, and then at 4 pints, there's, what, about a 20-point difference? So males and females in their attractiveness rating there's a larger space between them at 4 pints compared to 0. So you can do your interactions looking between genders at each level of pints, or between points for each gender. You can do it either way. But the important thing to take away from all of this is the interaction is simply comparing means within the cells. whereas main effects compare the total means that average across the other IV. Okay, that's probably the most technically complicated part of today. So if you got that, you're doing well. Now, that's all good and well, but looking at those means and standard deviations tells us nothing about skew or kurtosis. So we need to create a new variable that actually combines our two categorical variables together to create a single IV with 6 levels. And what this is going to do is it's going to allow us to then look at all 6 levels. So to do this, we use theegen command. We put in a new variable name, anything you like. You could write I hate statistics if that's what you want to write. I chose to use cell because I'm boring. Egen, a new variable name, cell, equals, now you need to write group, so that's an actual command, and then in brackets your two categorical variables. So egen, new variable name, equals group, brackets, sex, pints. And that's going to create a new variable called cell that will have 6 levels representing our 6 levels, our 2 genders at each level of pint. So I have this new variable called cell. If I look at my data, people who got a 1 on cell had 0 pints and they were male. People who get a 2 on cell, 2 pints and male. 3, 4 pints and male. Those coded 4, 0 pints and female. 5, 2 pints and female. And then 6, 4 pints and female. So cell has effectively now created a single categorical variable that represents our 6 inner cells. We can then use this tab stack command with attract by cell to now get our skewness and our kurtosis. And so I can see my means that we were looking at before. So really we could have done this, but the other table is just easier to read. We can see our standard deviations all together. And then we can start to look at skewness and kurtosis. And what we can see is that within the males, so our first 3 are for males, our seconds were for females, the standard deviations for males look like they're pretty close together. For females, maybe there's a little bit more variation. Looking at skewness, it does look like it's all over the place a little bit. Females seem to have more skewness in their data than males. And kurtosis, they all are a little bit platycodic. But we do have an n of 8, so we don't have, like, this is a little n of 8. So we don't have a massive sample size, so platycodic distributions aren't too surprising. So despite the fact that normality looks pretty dodgy, we haven't done a formal assessment. We obviously haven't looked at histograms or Shapiro-Wilk. Please, I would be doing that if I was you. But for the sake of time and because we've done those together, let's just move on to equal variance. And we can see that equal variance actually comes out perfectly fine. So remember last week we said to look at W0. The p-value is above 0.05, which tells us that our standard deviations are not significantly different from each other within the margin of error. Okay, this is good. Let's move on. Let's fit our ANOVA.